Yeah, hello, everybody. As some of you may know, I was a student of David Rowe in the 70s, and together we published a few papers on nuclear collective rotation motion using canonical transformations, spectrum generating algebras, and conventional cranking models. After that, I joined Atomic Energy of Canada, doing analysis, accident analysis on nuclear reactors for many, many years until I retired. I was very happy to retire and resume my physics research. But I was really inspired. Oh, sorry. I was really inspired by David Rowe's passion for understanding nuclear collective rotation or from a microscopic level, and it inspired me to really, especially in his book, he mentioned that he emphasized that there is a need to develop a microscopic version of the conventional cranking model. So in this presentation, I'll describe such a model and compare its predictions. Oh, sorry. And compare its the prediction of this model with the conventional cranking model for light nuclei. The conventional cranking model is given by this Hamiltonian, Schrödinger equation, where H sub naught is a nuclear Hamiltonian. Sigma here is the angular velocity multiplied by the angular momentum vector. This model is quite used often by nuclear physicists to predict the properties of deformed nuclei, and it does a good job. However, the model is semi-classical and phenomenological. In particular, the angular velocity here is a constant parameter. So therefore, this Schrödinger equation is not time reversal invariant, and also it's not even D2 invariant. So it's desirable to, as David was saying a lot, it's desirable to derive the model microscopically and reveal the underlying assumptions and approximations. So in this presentation, I'll describe a microscopic self-consistent cranking model for triaxial rotation, similar to the conventional cranking model, but it includes correction terms. I will compare, and I will also compare the rotational properties predicted by this model and this model for light nuclei. So we derived the microscopic model using a rotated degenerate nuclear state phi, given by the application or action of the exponential rotation operator e to power theta dot j on a deformed nuclear ground state. Substituting this phi into this Schrödinger equation here for the ground state, we obtain the transformed nuclear Hamiltonian given by this expression here, where each of the three terms here contains the gradient of the rotation angle with respect to the nucleon coordinate multiplied by angular momentum operator. This term, the second term here, also includes the linear momentum of individual nucleons. Therefore, this term here represents the interaction between the rotation and intrinsic angular moment, intrinsic motions. This term can be very complicated function of angular momentum and shear operators and all that, intrinsic properties. We make the angular moment, the transformed Hamiltonian here quadratic in the angular momentum by choosing the rotation angles, the gradient of rotation angles with respect to the nucleon coordinates to be given by the rigid flow velocity field, where each of the three matrices chi is antisymmetric. This is a nucleon coordinate. The rotation angles are also chosen to be given to be canonically conjugate to the angular momentum operators. Then the transform Hamiltonian becomes simplifies to this expression here, where I here is the rigid flow moment of inertia, principal axis components of the rigid flow moment of inertia. Oops. Okay, the second term here contains the off-diagonal component of the quadrupole moment tensor. Since this Q is much smaller than the rigid flow moment of inertia, this term is quite small and neglected. So the transform Hamiltonian reduces to the Rowe Hamiltonian, except that the angular moment of inertia in the Rowe Hamiltonian is now the rigid flow moment of inertia. We can show easily that the Hamiltonian, this Rowe Hamiltonian is intrinsic. That is, it commutes with the rotation angles. Finally, we derive the microscopic model by replacing the rigid flow moment of inertia by its expectation value, because the rigid flow moment of inertia is large and varies slowly with the angular momentum. We then apply the Hartree-Fock mean field method to the Rowe Hamiltonian to obtain this Schrödinger equation, where the first term is the Hartree-Fock cranking Hamiltonian, given by this expression here, which is identical in form to the conventional cranking model Hamiltonian, except that now the angular velocity is given by the angular expectation value of the angular momentum divided by the rigid flow moment of inertia. And because of that, this Hamiltonian is time reversal invariant and D2 invariant as well. The second term in this equation is the residual of the two-body interaction. Its mean field part is in the Hartree-Fock Hamiltonian, cranking Hamiltonian. The third term here is the residual of the square of the angular momentum divided by the moment of inertia, rigid flow moment of inertia. We solve the model equations for the microscopic model and the conventional cranking model for a deformed harmonic oscillator potential by solving Newton's equation for the cranking Hamiltonian, and to obtain this cubic characteristic equation for the normal mode frequencies alpha sub k, because the quantum and classical normal mode frequencies are the same. The intrinsic energy is then given by the normal mode frequencies multiplied by the total phonon numbers in each of the three directions. The expectation value of the angular momentum is given by this expression, which is obtained from this Hamiltonian, and the expectation value of the quadrupole moment is given by this expression. The potential, the harmonic oscillator potential, the deformed harmonic oscillator potential is made self-consistent by minimizing the intrinsic energy with respect to the frequencies of the potential, subject to the constant volume condition. For the conventional cranking model, we obtain the orientation of the angular velocity by minimizing the intrinsic energy with respect to its angles and adjusting its magnitude to satisfy the angular momentum constraint on the wave function given by this expression for triaxial rotation, and given by this expression for uniaxial rotation, where J is the imposed angular momentum. For the microscopic model, we get self-rotation simply using this equation, because this equation determines the angular velocity completely. However, for forced rotation, as in the conventional cranking model, we obtain this expression for the square of the magnitude of the angular velocity simply by squaring this equation, where the expectation value of the angular momentum is given by this expression for triaxial rotation and this expression for uniaxial rotation, uniform rotation. So we solve these algebraic equations, model algebraic equations, by solving them iteratively. Oops, what's happened here? Something is wrong with the conversion. Anyway, these are some of the results. The conventional cranking model predicts that the rotation is uniform because the angular velocity vector and the angular momentum vector are parallel to each other. But in the microscopic model, the rotation is wobbly and it's non-uniform. So both models predict that the excitation energy increases and the intrinsic energy decreases with the angular momentum and the quadrupole moment and the angular velocity. This implies that the increase in the rotational energy is supplied by the corresponding decrease in the intrinsic energy via changes in the kinetic and deformation energies. Therefore, holy cow, what is this? Therefore, when the angular momentum decreases, the angular velocity also decreases, and this eventually reduces the angular momentum to zero. This positive feedback between the angular velocity and angular momentum renders the cranking model rotational states inherently unstable. An angular momentum constraint on the wave function provides a negative feedback needed to prevent the rotational collapse, but only for one of the components of the angular momentum. This rotational instability is the consequence of the strong coupling between the intrinsic and rotational motion generated by the self-consistent conditions, and therefore this instability is characteristic of all mean field self-consistent potentials and not just harmonic oscillator. Therefore, the cranking rotational motion generally tends to be along one of the three components of the axis. I don't know how to raise this. Okay, there is another, and okay, let me to the next one. Normally, because of the instability, the third component of the angular momentum reduces to zero after a few iterations planar rotation, as shown in figure Silicon 28. Here, the third component of the angular momentum is zero at the beginning of the iteration, and the first component of the angular momentum reduces to zero due to the stability, causing the second component of the angular momentum to increase to the imposed angular momentum. the nature of the rotation depends on the ratio of the second component of the angular momentum divided by the first component of the angular momentum at the beginning of the iteration. For this ratio equal to 1, the planar rotation is stable in the conventional cranking model. However, it is unstable in the microscopic model due to fluctuations in these components. Oh. Okay. Okay. So these fluctuations then amplifies the fluctuations in the second component of the angular momentum, reduces it to 0, causing the uniform rotation along the x-axis, and the switching from angular momentum wave function constraint for triaxial rotation to angular momentum constraint for uniform rotation. This quenching of wobbly rotation reduces the energy level spacing at J is equal to 8, improving the agreement with experiment as shown in this figure. This figure shows that okay. This figure shows that the two models predict that the excitation energy is similar at up to J is equal to 6. Above J is equal to 6, the conventional cranking model predicts that the excitation energy continues to increase above the measured excitation energy. However, the microscopic model predicts that the excitation energy levels off and falls below the measured excitation energy. At J is equal to 8, the neon nucleus becomes actually symmetric about the rotation axis and the rotational band terminates. The discrepancy between the measured and microscopic model predicted excitation energy is due to neglect of the spin orbit interaction, which we have shown to increase the excitation energy by about 10%. The remaining discrepancy between these two energies is due to the neglect of the residual of the square of the angular momentum and the two-body interaction, and we have shown that to increase the excitation energy by 1 to 2 MeV, causing the predicted excitation energy to be very close to the measured excitation energy. Okay. Okay, this figure, I don't know what's happening here. No, before that. No, before that. No, before that. Before that. Okay. Okay, that's fine. Okay, so this figure shows that the quadrupole moment that the two models predict similar quadrupole moments up to J is equal to 6. Above J is equal to 6, the microscopic model predicts that the quadrupole moment decreases sharply below the measured excitation energy because of the transition from wobbly rotation to uniform rotation. Let's see if I can. No, I don't understand. Okay. Okay. For back. Yeah, back. Okay.
Just use the arrow keys here to move your slides. This one back and forward.
This one.
This one should. It's just a.
Okay. Anyway, for the ratio of the angular momentum components not equal to 1 in neon 20, the model predicts that the wobbly planar rotation at low values of J, it predicts wobbly rotation, planar rotation at low values of J. At higher values of J, the triaxial rotation, I don't know what's here. Neon becomes triaxial. Neon becomes triaxial, and the rotation becomes uniform along the x-axis for the ratio of the angular momentum less than 1, and along the y-axis for the ratio greater than 1. At J is equal to 8, the neon nucleus becomes axially symmetric about the x or y-axis, and the rotational band terminates. For magnesium 24 and silicon 28, for late magnesium 24 and silicon 28, the model predicts similar results as in neon 20, except that in silicon 28, the microscopic model predicts that the band terminates at J is equal to 12. However, in the conventional cranking model, the band does not terminate. For triaxial magnesium 28, the microscopic model predicts steady triaxial rotation up to J is equal to 6. At J is equal to 8, the magnesium nucleus and its rotation becomes axially symmetric about the y-axis and develops a nutation and deformation, and the deformation becomes oscillatory with its rationness, as shown in as shown as here. The angular momentum is axially symmetric about the rotation axis, but it's oscillatory, and also the angular momentum along the x-axis is oscillatory. The quadrupole moment, yes. The quadrupole moment. One more. No. Yeah. Okay. Where was I? Nutation. Yeah. Okay. So this rotation in this oscillation in the rotational motion may be considered as transitioning between two coexisting minimum energy states about 0.5 MeV apart. At J is equal to 10, the magnesium rotation becomes steady, and at J is equal to 11.5, the magnesium and its rotation becomes spherically symmetric, and the rotational band terminates. Now this is the calculated angular momentum, and instead of being 12, it is 11.5 because of the relaxation of the intrinsic state due to the self-consistency between the angular momentum and the angular velocity. In contrast to all this, the conventional cranking model predicts a steady uniform rotation of triaxial magnesium 24 along either x or y axis. Please. More. Okay, one more, please. Yeah, this figure shows the quadrupole moment for the magnesium 24. It shows that in the microscopic model, the quadrupole moment above J is equal to 6 decreases sharply and becomes negative. This is due to tumbling and rotation of the magnesium ellipsoid about one of the principal axes. This occurs only for certain values of the ratio of the angular momentum components. For other components, the quadrupole moment decreases, but it remains positive. Going back. Okay, for silicon 28 at j is equal to 2, both models predict that the planar rotation transitions to uniform rotation along the y-axis at a fixed value of j, or it's a fixed value of 2 for j. However, the angular velocity and the quadrupole moment become oscillatory, since the angular velocity increases and decreases at fixed value of angular momentum. The rotation resembles a figure skater's fast and slow spinning, where the oscillations in the quadrupole moment replaces the skater's expanding and collapsing arms. A nutation may also be imposed on this rotation. This rotational mode may be interpreted as a coexistence between two neighboring states of different deformations. Okay, could you repeat it, please? Okay. In conclusion, we have derived a microscopic self-consistent cranking model Hamiltonian for triaxial rotation, similar to that of the conventional cranking model. This similarity is made possible by using rotation angles that add collective rigid flow velocity field to each Newtonian momentum, linear momentum, and decouples the rotation and intrinsic motion, yielding a self-consistency between the angular velocity and angular momentum. The model equations are solved in closed algebraic forms and solved iteratively. The rotational states are unstable and decay to zero unless it is prevented by an angular momentum constraint on the wave function. The instability is stronger in the microscopic model due to self-consistency between the angular velocity and angular momentum. The instability results in various nuclear shapes and rotational modes and transitions at different j values. The rotational mode transitions change the rotational excitation energy, rotational excitation, and the quadrupole moment. In the microscopic model, the residuals of the angular momentum, of the square of the angular momentum and the two-body interaction increases the excitation energy closer to the measured excitation energy. In future, we would like to study the model differences for other nuclei and for more realistic interactions, and study the effect of vibration on the rotational motion. Thank you for your attention. Sorry about the quality of, there's something went wrong with, transition from board to